Guys, so today we are going to be working on solutions. As you can see, I am going to be doing a little bit of a demonstration for you, and then once we are done with that, we'll go ahead and move into defining what a solution and a mixture is. Okay, so to warm up, I want you guys to look at the components that you see on the board and see if you can list those, categorize those as either a solution or a mixture. Do the best that you can, take 5 minutes, and then we'll come back and we will define what a solution and a mixture is. Okay, so a solution and a mixture, they sound pretty similar, but they're actually two different things. A solution is a uniform mixture of one or more solutes that are dissolved in a solvent. We haven't defined what a solute and a solvent are, but basically what you need to know about a solution is that something is being dissolved in something else, and if a chemical reaction is occurring, it is a solution. A mixture is when two or more substances are combined, but they are not being dissolved in one another. They can be separated by physical means after they are put together. So from that demonstration that we did, what do you think is, which example from the demo is a solution? And which example from the demonstration do you think is a mixture? All right, so let's go back to that warm-up question now that we know what a solution and a mixture are, what the differences are. Let's kind of review that warm-up question, starting with salt water. So salt water is going to be a solution because we have salt amongst a few other different vitamins, minerals that is dissolved in the water. Powdered lemonade. So when we make lemonade out of a powder, we add the powder to water and we dissolve it, and that's what gives us that yummy lemonade. Bleach is a mixture. It is a mixture of a bunch of different chemicals combined to one. Nothing is being dissolved in one another. There's no reactions happening. It's just kind of like a combination of a bunch of different chemicals. Same thing for cement. So we're just kind of combining a bunch of different stuff into one in order to give us that like liquidy component that then hardens later. Coffee, what do we think coffee is? Right, it's going to be a solution. So when you're making coffee, you start out with like coffee grounds, and those coffee grounds are then dissolved in like a lot of hot water, and it gives you the solution that you're able to drink. So you're not getting like powder grounds or anything in your coffee. Blood is going to be a mixture. So it's more of like a combination of a bunch of different things in your blood. So nothing is being dissolved in one another. There's no chemical reactions happening in your blood. It's just a mixture of a bunch of different components. And the last one is fog. Fog is also a mixture. That's also just a combination of a bunch of different things in the air. No reactions are happening. Nothing is being dissolved in one another. So it's going to just be a mixture. Alrighty. So moving on, we need to define what solute and solvent are. So we kind of touched on that a little bit when we were defining solution. So a solute is the substance that is being dissolved. It is that powder or the solid or that whatever that's being dissolved in another substance. The solvent is the substance that's doing the dissolving. So let me draw you a little picture here real quick. If we have a beaker, you can't see that. Let's do black. So we have a beaker of water. This is water here. That's going to be our solvent because we are going to add something to that. Let's just start with, I don't know, salt. NaCl. If we add NaCl to this water here, that salt is going to be dissolved. It's going to give us salt water. So this is the solvent. What is doing the dissolving? That water is going to be dissolving that salt water, or that NaCl. The NaCl is going to be the solute. That is what is being dissolved by the solvent. So then when we add that NaCl to the water and it's dissolved, we get a solution of salt water. And then for concentration, concentration is going to be the amount of solute per measurement of solvent. So, for example, one of the most common concentration that we use is called molarity, and that's going to be moles of solvent per liter of solute. And we're actually going to talk about that a little bit later, so I'm not going to get too much into that. All right, so next we're going to talk about different types of mixtures. So we have heterogeneous and homogeneous. And basically, heterogeneous means that a solution is not going to be the same throughout. Things are going to be a little bit different. It's not going to be uniform. There's a few examples here that I listed. One would be a bowl of Fruit Loops. I mean, that's not going to be the same throughout. Obviously, you're going to have little pieces of cereal and you're going to have milk. Another one is mixed nuts. I mean, your bowl of mixed nuts is not going to be completely the same throughout. You might have more cashews than you have almonds. It's going to be a little bit different throughout. And then a homogeneous mixture is going to be the opposite of that. You're going to have something that is the same throughout. It's going to be all the same proportions of each component. One of those is air. So air has the same exact proportions of its components all throughout. If it didn't, we probably wouldn't be able to breathe it. It might probably kill us. This next slide has a little bit more of an example for you guys. Oops. No, this picture. I'm going to draw you guys a picture. Sorry. I thought that slide was in there. Okay, so a homogeneous mixture is going to look something like this. You're going to have the same proportions of components throughout. So here you can kind of see that the blue and the purple components, although they're a little scattered, they're still the same proportion. So there's 6 of each there. So it's going to be the same throughout. A heterogeneous mixture is not. So let's go ahead and do this. And we might have like 4 or 5 of the blue, but we might only have 1 of the purple. And so obviously the proportions are not the same. It's not the same throughout the entire mixture. So that's going to be a heterogeneous mixture. All right. Moving on. Saturated solutions. So a saturated solution is when a solution has the maximum amount of solute that it can in that solvent. If you add anything more into that solution, it's not going to dissolve. A supersaturated solution is when the solution contains more of the solute than what can dissolve under normal circumstances in that solvent. And so you might wonder how you can get to that. One way is by heating the solution. So if you have, let me think. I think the max concentration for a saltwater solution is 5 molar. So if you have that solution, it's already dissolved in your water. If you want to add a little bit more, the way you can do that to get it to go into solution for it to actually be dissolved in the water is to heat it. When you heat it, it'll dissolve the rest of that salt and it'll go into solution. Any questions so far on anything that we've covered? All right. So we're going to kind of talk about solubility and molarity a little bit. Starting with solubility, that is basically, solubility is a way of defining how easily solutes can go into solution. So the more soluble something is, the easier that solute is going to be dissolved in its solvent. The less soluble that it is, the harder it's going to take to get that solute to go into solution. Some certain ways, if something is less soluble than you want it to be, if you're trying to get it to go into solution and you're having a really hard time with it just kind of going by itself, some ways you can increase the solubility is increase that temperature, agitation, stir it, shake it, get it moving around. That'll help it go into solution a little bit. And also with a pressure increase is going to help that solute go into solution as well. All right, so moving on to molarity, that's the concentration that we kind of talked about a little bit earlier. And I did say that it's going to be moles per liter. That's how we measure concentration with molarity. And so that's going to take a little bit of math. So we're going to kind of do a few examples just so you guys can get an understanding of it. And then we'll do a little bit of practice. Okay. Let me just get this board erased here. All right. So the first example, we're going to do iron chloride. The question asks, what is the concentration of an aqueous solution with a volume of 450 milliliters that contains 200 grams of iron chloride? And so basically we're looking for the molarity, the concentration of that solution. And as I said earlier, here we go again, molarity is moles per liter. So the first thing that we need to look at is we need to get moles and we need to get liters, and then we'll be able to do our math. The example gives us a volume. It says 450 milliliters. That's not in liters, so we have to convert that, but we're going to save that for later. That's an easy step. The problem also does not give us moles, right? It gives us grams of our iron chloride. So we need to convert from grams to moles. So we know that iron chloride is going to be, this is the equation for iron chloride. And then we have to find the molar mass of that, right? We know how to convert from grams to moles. So we know that iron chloride, that molar mass is going to be 126.75 grams per mole. That's the molar mass, all right? We know how to write that. So we know that. So we're going to start with 200. The problem gives us that we have 200 grams of iron chloride, right? And so in order to convert from grams to moles, we divide by the grams, right? Because we have grams here. So what we're going to do is multiply by that conversion factor. So 1 mole over 126.75 grams, right? So that molar mass is kind of our conversion factor here. So we have 200 times 1 mole over 126.75 grams. And so that math is, anybody have the answer to that? Equals 1.578 moles of iron chloride. All right, so now we have moles, right? So for molarity, we need to do moles divided by liters. So we have this divided by our liters. Remember that they only gave us 450 milliliters. So that in liters is going to be 0.45. 0.45. So that math, the moles divided by liters, is, anybody have the answer? Right, so we have 3.51 as our concentration. So that's how we're going to do that math. Okay, so next example, let's see if you guys can do it by yourself. minutes. All right, what's going to be our moles that we have in this example? Right, 2.13 moles is what we get from the grams that they give us. So then when we divide 2.3 or 2.13 divided by 2.5, the liters that they give us in the example is 2.5. And then so the math there, we get what? Right, we get 0.85 molarity for that one. All right, we're going to skip example 3 because it's another... Yeah, it's another similar one. So we're going to move on to example 4 to save us a little bit of time. So example 4, how many liters of a 4 molar solution can be made using 100 grams of lithium bromide? This one's a little bit different. So we know that lithium bromide, its molar mass is 86.845. We calculate that by using our periodic table. So this one isn't asking us for a concentration. Our concentration is already given to us. We need to use that concentration in order to determine the amount of liters that we need. All right, so in order to do that, we should calculate moles with our lithium bromide molecular mass or molecular weight. So we have 100 grams, they give us that, and the moles of that is 845 equals 1.15 mole. Everybody get that? 1.15 moles. All right, so now we have that. We need to find liters. So in order to do that, we need to use the concentration. And the concentration is 4 molarity. So when we have 1.15 moles, we're going to multiply it by that. We know that concentration is moles per liter, right? So we're going to flip-flop that so that our moles cancel out and we get liters. So when we do that, we have something that looks a little bit like this. So we flip-flop the 4 moles per liter and we have 1 liter over 4 moles. So when we do that math, these moles will cancel out and we're left with liters, right? Does everybody understand that? All right, so what's the math for that? How many liters do we need? All right, so we need 0.288 liters. That's how much we can use in order to make that concentration with 100 grams. Does anybody have any questions? Does everybody understand what I just did? Alrighty. So if everybody understands, we're going to skip number 5. Y'all are going to have a chance to kind of work on some of these problems by yourself while we're here. So you can ask me any questions if you get stuck with any of the math or whatever. And we're going to move on to a little fun lab that I have planned. It involves candy, so that's going to be fun. So go ahead and get into your lab groups, and I'll kind of explain what we're going to do. Everything's already set up on your lab benches. Don't touch it yet. I mean, it's candy. I know it's tempting, but don't touch it. I'll explain the instructions once we get into our groups, and then we'll go ahead and get started. When you're finished, I'll have already placed out that independent practice that I have planned for you guys with molarity. So you're going to get a chance to practice those math problems. If you have any trouble, you can ask me. So once you're done with your candy lab, get back to your seats, work on that. And then once we are finished, we are going to, with 5 minutes left, we're going to work on our exit ticket that we always do. So I'll give you 5 minutes to answer that question, and then that'll be that. Whatever you don't get finished on that independent practice, we're going to have that finished for homework that's going to be due next class period. Okay, so go ahead and get in your groups, and we'll get started on Candy Lab.